Norman or my office anymore. They're going to be in the old conference room in the old Kimby building. Same time, 12:50 to 2:45. So hopefully that's easier for people to get to. So that'll be starting next week. And then, so all I'm going to do today is go over an example in the book. It's 4.7 from the 4th edition, if you're rather curious. But it involves basically just sizing TFRs, CSTRs. It's a pressure drop section that they kind of cheat with, but and then there's some equilibrium. So this is kind of something that you might see on the test, or at least parts of these in different problems. But it's really not that bad. So it's going to take a minute to write that on the board. So this is an elementary gas phase reaction, and it's I think this is di-tertiary-butyl peroxide. Butyl peroxide, and then it's just decomposing into ethane and this guy. So you can just call them A, B, and C. It's isothermal. It's going to occur in a TFR, so tubular reactor. For the first parts, there's no pressure drop, and it also gives you a specific reaction rate of 10 to the negative fourth inverse minutes. And it gives you the activation energy because it's not going to be at the same temperature, the reaction. And so then if you draw the reactor, tells you the inlet pressure is 10 atmospheres. Initial temperature is 127.
Can you turn on one of the lights, another light in the front?
Yeah, I can talk louder too. And it tells you the entering flow rate is 2.5 moles per minute. And then what it wants you to calculate is the reactor volume at 90% conversion. So x equals 0.9. And so to start off with PFR, well, it starts off with calculate the volume of the PFR. So then with this, you can start off by, the design equation for PFR. You also know that since it's an elementary gas phase reaction, irreversible, the rate law is going to just be
I think we did this already.
KCA. Did you already do this in class?
Yeah.
That's not PFR, isn't it? B equals F.
I think the temperature was just different.
Isn't that
So this will become an integral, but yeah.
Okay, I was
when
going
you
to say
integrate.
that's CS2.
Yeah.
I think the temperature is different than we want to think.
Did you just do something very similar and just change
Like
temperature?
this 2.5, the 85 is there.
Is the K given for a different temperature?
Yeah.
I don't know why else they give us activation.
So The activation energy is so you can calculate using the Arrhenius equation, the K at T equals 127 instead of 50.
Is that K for, like, what temperature is that at K for?
Oh, my bad, forgot to write. It's at 50 degrees. So when did you guys do this problem? Two lectures?
Hey, I'm okay with you
You
going.
guys
Yeah.
want to see it again?
Yeah,
That's all I got.
That's fine.
Yes, if that's all you got. Then yes.
This or homework? Huh? All right. So. You did the stoichiometry table, which I wasn't planning on showing. Pretty simple, straightforward, it's the same for everything. Same set of steps. You get C naught over 1 minus x, 1 plus epsilon x. And you know that your epsilon equals the mole fraction of A times delta. In this case, delta is easy. It's just 2 plus 1 minus 1, so it's 2. And you only have one reactant, so your mole fraction is automatically 1, so this is equal to just 2. Then you can calculate this initial concentration because I think it tells you it's an ideal gas in the problem statement. So you can just use the ideal gas law, and you get C naught is equal to the initial pressure over RT. So now you know your initial concentration, you know your epsilon, and you have two functions of x and Ca. So you can go over and use your design equation, which does become an integral because it's BFR. Then you can just plug in for RA, and you get over your K Ca naught. And then this is an integral that I believe is in Appendix A, which you've already probably done several times in the homeworks in class. So that's equal to and then, so you know your conversion because it tells you 90%. You know your epsilon, you know your Ca naught, you know your Fa naught. K you have to solve for. Just to, well, you know a K at 50 degrees Celsius, so now you just adjust it for 127 degrees. So you can do that. Then your new K at 127 degrees comes out to be 0.044. So now you have everything you need to solve for your volume of the PFR. So this one is pretty much just a straight plug and chug with a little bit of thinking. Comes out to be 967 to plug everything in. The next part of the problem is then find the equivalent volume of CSDR, which is obviously a lot bigger. So your concentration is going to stay the same. Most of your relationships are going to stay the same. Just your design equation will change. So then, again, you know all of these again, so you can just plug it in. So you get something about 4 times bigger than your PFR volume when you switch it to the CSDR.